Thank you, Mary, for excellent introduction and then inviting me to Vancouver. Let me just clarify the title of the talk today, Architecture After March 11. I guess people know what March 11 stands for. That's the huge earthquake that Japan had 5 years ago. And that we lost quite a few people. Now, it's such a dramatic title that I wasn't quite sure if I should even use it. And I don't really frame my research around it. But I was talking to Mari yesterday, what kind of audience I'm going to have today. And she said, it's going to be a public lecture. And I was expecting a full of students. I wanted to see what the project I'm working on. But rather, I shifted it so that explaining why I do it, how I do it, and in the end, what I do it. But the what part perhaps is not so, it is important, but I thought it'd be nice to talk a little bit about the context in which all the research are taking place. Now, the picture we're looking at here is the Tsunami Wall. Is that a pointer? No? Okay. After the 9/11, the wall needed to be constructed in order to prevent the next tsunami to come. Now, that tsunami we had was magnitude 9.0 earthquake, and the height of that tsunami was about 16 meters. It's quite tall. Now, in order to prevent, they have to build this massive 400-kilometer tsunami barrier in order to protect the landscape. Now, it's understandable that they have to do it, but at the same time, are there any other way to do it? So, beautiful landscape, it's going to be covered with a massive wall. So, what would be the other options? But we meaning the government of Japan, they don't really have a time to explore, or they have an idea to try it out in a different way. They have to do it. It's just got this machine. The force has to be prevented with a stronger force. In this case, it's a massive wall. So they're building about 20 meters high of the wall. Now, I, as an architect, must be, thinking must be other way, must be other kind of option that we could explore. But once again, they have this machine as a modern, very efficient, very effective way to prevent next disaster. And we seem to have no option but to construct it. And the residents has also accepted the fact that they have to follow the construction process. So my talk today is about this conflict between the certain kind of effect that our society constructed seems very, very working well on one hand, but on the other hand, these little tiny, perhaps not so strong, but it's very weak and very pervasive that we don't even know they exist, but may have a potential to create something greater than, in this case, than the tsunami wall. Now, that was the incentive to start thinking about alternative to what we consider something major, something strong, something powerful. So together with Professor Kengo Kuma, I heard that he's coming next couple of weeks also to Vancouver to talk. Together with him and also Professor Manabu Chiba, we created this laboratory. It's called Advanced Design Study at University of Tokyo. The Tokyo University, unlike here at the North American university system where individual laboratory is based on the professor's interest. So whatever I wanted to explore, I set up in the studio, and I have 2 years as a graduate student to explore a series of ideas. And I'm going to explain a little bit later, but the problem of this is that we have very little fertilization. We don't really talk to each other much. We kind of stay in the cell within a laboratory. So we thought, why don't we address this issue that we have to deal as an architect for social conditions that we are living right now through a series of topics. So we don't have a pointer, but there's basically I'm going to talk about two of those main the research kind of unit that we created. The one's sustainable prototyping. Sustainability is a very important issue currently. Digital fabrication, how to engage formal making through digital computational processes, design practice, how do you embrace education also with industries, social design instead of architects are the one that design to provide in the design for the people. Can we reverse the process that people, local residents, they can design and we become facilitator for their visions and design possible. Design think tank, we just started this working together with developer to think about alternative way to develop the city where Japan, there's a tendency to wipe the existing conditions and put something new. Are there a different way to develop the urban conditions rather than scrap and build? And that's what they call. Media initiative, like this event, like a lecture series, or sometimes I'm sure that you guys have publication to University of Tokyo, doesn't have those public activities. So we try not to output the activity, but rather promoting what we do through a series of initiatives, like in a lecture, like in a publication. So we call it media initiative. So these are kind of activities that together with Kengo Kuma and Manabu Chiba, I'm trying to set it up. And many of the talk that I'm gonna be talking are not only about my work, but the collaboration between three professors and also participating students. Together with them, I'm going to be talking two issues today. One is architectural prototyping that comes out of digital fabrication, thinking through not only about how to produce through digitally or computational processes, but how to start thinking about what purpose or in the end, why are we making all these production process through the digital fabrication. So in the end, or at the end of the process, I believe it is all for the human being. So how to include the human as a part of digital fabrication processes. And the second one I'm going to be talking is the urban prototypes. That maybe I should explain it. Digital fabrication, I primarily explore that with my first year student. And the urban prototypes, I worked that together with second year student. So student will develop the first architectural idea through the structure, fabrication, assembly processes, materiality, geometry, a kind of very limited issue that what we consider architectural conditions, then move that into urban condition that is a lot more complex, dealing with economy, the site, program, and all these things that makes architecture as a complex system. So I'm going to be primarily focusing on architectural prototypes, but then see how those research idea, fabrication idea could be tested at the condition of the real site as real, the cultural conditions. Now, I thought it'd be nice to talk a little bit about so you understand how it works. So typically in North American architectural schools, studios are taught in semester base. So it's about 12 to 13 weeks. And I have taught in different places here in the US and also not in Canada, but North America. It's a very difficult to explore ideas with such a short period of time. So typically I said 8 weeks of analysis and research. You know, here's site analysis, program analysis. Student will work a lot. What are the issues that they have to deal with? Then output of design is very little time to develop, and oftentimes just one idea, test it out, and that's it. And then you go into the next studio, different set of criteria, different professors, and different outputs. So very difficult to develop the idea, but you get a sample of different ideas. At the TADS, this is Tokyo University Advanced Design Studies, instead of these, not in a bad way, but kind of wine tasting way of learning architecture, perhaps we can develop the large one project through a series of interrelated projects that consistently work from very bad idea to good idea. If you keep working on it for over and over and over again, maybe you can develop the idea. So just to quickly explain, everyone in my first year student, the output of that is to construct a pavilion at the large scale, which I'll show you later. But when first year student, they come to my laboratory without doing anything, they start making the pavilion was designed by a previous first year student. So when they come the first, they get to experience what student worked on the previous year. And together with the second year student, so that's how they hand it a knowledge and also get to know what are the kind of project that we work on. And then the first year, then they start working on their own set of architectural prototype. In this case, is output towards the pavilion, construction pavilion. And then towards the end, I wonder if there's no even cursor. The student will work together with the second year student on their thesis project. So in this way, one of the idea is how to make architectural education evolve rather than architectural education keep repeating the same thing over and over. Like my teaching side, we always give out the studio project. For students, it's always new. So for the student, it's a kind of exciting, but from teaching side, we have to keep coming up with a new idea. And how do you set it up so that a project evolves and gets better, and I don't really have to do anything, but the student, they understand. So when they come first, they experience, and second year student will teach first year, and the project, because they build it with their hands, they need to know, they already know what they have to do in order to make it better for the second time. So the program is already created its kind of momentum to evolve from the simple to the complex. So let me just quickly go through a digital fabrication lab. That's what I was saying, architectural prototyping. This project is funded and also worked together with 11 sponsors. I have to negotiate and bring money to the program in order to buy equipment. Like here, I assume that you have fantastic digital fabrication facilities. We don't have anything. So in order for us to do, I have to bring money and the purchase. So sponsorship, but they don't necessarily just give you for free. I have to say, let's work together. So in the end, we collaborate to develop the pavilion together. Just to give you a quick context, as Mari explained, before I came to University of Tokyo, I was a co-director of Design Research Lab at the Architectural Association. And this is towards my last years of AAA, 2008, when digital fabrication became possible to create a large-scale construction. So in this case, a laser cutter instead, a water jet cutter that cut through the concrete, all these fabrication equipment. And we thought, why don't we try it out? So this is a kind of large model that's too big to call it model, but it's too small to call architecture. So the idea is, how do you explore the idea of digital fabrication, not through the making model, but the large, and of course the issue of scalability, structure, and also assembly processes. In this case, this is a design done by a graduate of AA, and the students are asked to put together this building or this giant model in about 3 weeks. We also collaborated with a structural engineer, Adam Taylor. Let me just quickly go through. The point is, we fabricate it, design it, just like we're going to make a little tiny model. And it works beautifully at the model scale, but when students are trying to put together, we thought we can finish in 2 weeks. In fact, it took us 3 months. In the meantime, students couldn't do anything because it was their spring break. I said, okay, let's put it up in spring break. But it ended up a whole semester putting this giant model together. So this is the kind of contrast between the model, half day, and this one. Every bit of it, if it works well, I think it goes, but because the students are putting together, and some of them are, say, a meter span with a little tiny, say, notch, and it's a bit of an off, in the end, nothing matters. It's like a giant 3D jigsaw puzzle. So what we learn in this whole possibility of digital fabrication is it works really well. Geometrically, you can optimize structure and also the cost effective because cutting straight line, the curved line, the same cost and all that. But there is a discrepancy between accuracy of machines and accuracy of human. This could be the problem or could be an interesting place to work on. So when I came to Tokyo 2010, I thought, why don't we use this discrepancy as a point of departure for series of research? So instead of human are the one that constantly making mistake, why don't we develop a system that observe all those discrepancies? So the first one I tried was using this called shrink wrap, like these drinking bottles with the labels and all that. Like when you heat it, this plastic shrinks. So the material has an ability to adjust these differences and discrepancies. So this case is creating minimum surfaces. That also works as a structural. Very crude. The student can build this by hand, but the structure, it's not depending on accuracy of all the parts, but rather the material has an ability to adjust its size. So you can see the students heating the material in order to make the things to get very taut structure. But the first one was very crude one, and there's very little to control the geometry. So in order to have a better control of the output, instead of giant frame, this time we use a series of circle pack made out of bamboo. That, in this case, if you were to control the geometry, all you need to do is control the shrinkage. The smaller it is, the smaller shrinkage, the larger shrinkage, and that would generate the geometry. So once again, how to use these loose fit between geometry and also the accuracy. In this case, the material is the one that making all these adjustability possible. And I was talking to Toyo Ito, the architect in Tokyo. He said something very interesting, that he thought more advanced computational use of design that makes it easier at the construction site because everything is, in fact, being perfectly designed, and all you have to do is just put it together. And perhaps less skilled labor can be perform those kind of complex project because of the support. But in fact, completely the other way around. The more advanced, the computationally advanced project, the higher skilled laborers are required. So it's an interesting the discrepancy here as well. So with that, this is the first project I worked together with a construction company, so Obayashi Corporation. With this project, I made in a pitch with a construction company because they're facing, this is Japan where the population of age over 60 would be about 40% in about 10 years. This is a staggering number. The younger people are disappearing, but the more and more the senior citizen, if that's the right word to say it, but the over 60 are becoming major population in Japan. So how do you deal with the construction crew that they have to secure? And that becomes a very crucial issue in all the construction industry in Japan. The other thing is about the technology and also the carpentry, a tradition and skill that exists in Japan. And those are also disappearing too. Used to be like this person is a national treasure. The person can be national treasure. It's kind of amazing things in Japan. That he has an ability to produce very intricate, very precise carpentry work. But those skills are also disappearing. What do you do about that? So the one answer would be maybe we can turn everything into the computational processes. Or maybe we can find an alternative. But at this time, with this project, we thought, why don't we do all these complex processes that can be achieved through a digital fabrication? I'm just going to quickly go through this, because I'm not sure how much time we have. So this project used very thin stainless steel. It's a 0.10. It's almost like a Coke can. That's the kind of thinness. But if you put it together in the right way, those thin material could become a structural. So how do you deal with the lightness and also strength? But at the same time, maybe I would just go back. At the same time, the structure in this case, a tensegity structure where compression and tensions are all balanced. So I don't know if you know the tensegity, the strength is not depending on the material strength, but strength is depending on the balance of components that put together. So the students are also developing this tensegity structure, typically done it more three-dimensionally, in this case, as in a surface organization that creates a dome, that the dome geometry makes the structure possible. So we work quite intensely with the digital simulation in order to generate this geometry. But the key part is, here's the cursor, is that instead of just regular dome, we made this inside, it's like half a donut, and in the middle it's a floating, that becomes a counterweight. So this counterweight is always pulling that whole cable down in order to make the geometry always in tension. Tensegity requires tension, but because the material is quite thin, we couldn't stretch it too much. So we found a way to make this a balance of the geometry and the material strength. Now, just going back to the whole issue of, I was saying earlier about discrepancy of accuracy and also, in this case, the stability, it's being compensated through the geometry, and in this case, it's in the counterweight processes. So together with Obayashi, the company, the staff, that we work together quite closely. And the first is to simulate, how do you make this seemingly surface-like material, but at the same time, when it becomes, in this case, the dome becomes very tight and very structurally balanced. But we also wanted to try it out. This is some sort of temporary structure that could be folded up like an accordion and brought to the site in different places and put it up again like a pop-up structure. And so it has this ability to be collapsed, open up, and then put it up again. And how do you actually develop that? An interesting thing about this is that you have to look at the structure in so many different ways that while you're lifting, it has very different structural forces acting upon, but at the same time when it's say stabilized or constructed, it has different forces acting. So structural simulation requires the different stages of construction processes and also the final form as well. Let me just quickly go through. So this is a series of testing of how this very light, very fabric-like a structure lifted and become a dome. It will become very tight construction. So is a simulation that allows for us to explore the geometry and then construction processes. Let me quickly go through these as well. So in order to test it, this is a 1 to 5 scale models within our laboratory. So all of it could be collapsed, brought to the site, and then lifted finally with this crane. And a very simple kind of stitching of these seam allow for the geometry to be very stable. This also requires very precise lengths of these components are put together by a series of cable. So once again, everything is quite manual, but the manual labors are being supported by the digital fabrication. In this case, is creating a jig. From the diagram and the fabrication processes. And those are the dynamic system where we have to make the structure, once again, not the strength is based on the material, but strength is based on the geometry. So all the dynamic forces that we needed to calculate. I'll just skip that. So that's I was talking about this in the middle of the geometry that pulling down towards the middle allow all those components to be balanced and also becomes quite stable in the end. Some of the structural calculations. And also working together with the structural engineer, his name is Jun Sato, that he does most of his work for young upcoming architects. So within our structural lab, that we have to crush it, many of those. It's very thin, as I said, very thin stainless steel. But when you inflate, it becomes like a pillow that becomes a compressive element. Video that shows fabrication assembly processes that I think. Now, what we learned from this process was, you saw the robotic arms that we developed for stitching. I call it stitching because you cannot weld together stainless steel without having some sort of primary support. Otherwise, it's just going to get all warped. So we developed the whole digital fabrication around this armature of the arm. But what we learned from that, I don't know if you noticed, towards the end, this whole fabrication, we had about 20 people working on it. And they are expert, and one of the best contractors that we have, not just the contractor, the people who actually put together the building. Without their support, we probably couldn't build this thing in the end. So what we realized, the human in the end, once again, is the crucial element within this digital fabrication. So we turn around and said, why not not turning a person into pressing button for the digital fabrication, but we support the people in order to augment their capacity through the digital fabrication to construct, in this case, the pavilion. So the next project is using 1 million chopsticks in order to build. This one is, why not look at the 3D printer more critically? And I'll show you in the video, but typically 3D printer is an excellent to produce all these complex geometry, anything that you imagine, but at the same time, you can only build the parts if you wanted to apply an architectural scale, or you make a giant 3D printer on site, which seems not very feasible beyond a certain scale. So we thought, why don't we develop a personalized 3D printer? It's distributed, so everybody has their printer, and you have to go and print it locally, but if they're all network, it could act as a single 3D printer. So this is the, using 1 million chopsticks, so we printed it. But you use the chopstick because chopsticks, unlike in the regular granule, which if you just put a sand, they always make a 34 degrees, like in a mountain. But chopsticks has an ability to aggregate. So depending on how you drop them, it could go curved, it could go straight up, and you can control so many different ways. So this is together with a Shimizu Corporation. They were quite suspicious at the very beginning because we thought we're going to make a pavilion out of chopsticks because they like to make things very straight, nice and clean. This is all about fuzzy. You're not quite sure what the strength of the material is and everything, except what we got at the chopsticks. So, but we convinced them this is the way to go. So here's a kind of quick a video to show the concept.
With modern technology, we see two major trends. One is human augmentation, information distribution systems and devices that enhance physical capabilities. Another is the development of large-scale 3D printers. Our approach is to integrate these two trends by creating what is basically a network of human-driven 3D printing devices, which we call STIK, STIK. The basic component for the system is a simple stick, squaring section. However, by controlling the way that these sticks are distributed in a large quantity, we can observe emergent logic in the way they form structures. We have found that the structure does not have a specific breaking point. It distributes a series of local failures while remaining intact as a whole. The scanning system monitors the stick structure, sending data to the network, which is compared to the digital target geometry in real time. The network then feeds back to each distribution node, acting as a guiding system, allowing stick dispensers to work collaboratively to function as a single large 3D printer.
So instead we take everything out, we thought, why don't we develop this feedback in the real-time scanning system so that when people make a mistake, it's not a mistake, but it just needs to be recalculated for the new targeted geometry, but new target geometry also needs to be rescanned with the structural analysis. So these are the kind of monitoring to see how the geometry is constantly changing, but the mistake are always being adjusted within analysis of the structural development. We saw that in the video. It's an interesting thing about this professor was wondering about how do you make a strong and safe building, but at the same time it doesn't have so much weight. Because in order to, this is in Japan, that in order to make a safe building, you have to make a span of the concrete, or oftentimes becomes very heavy. But when the failure of those buildings, the disaster is multiplied. So the lighter buildings perhaps has a less a potential kind of disaster consequence. So he's developing this whole idea as a porous, lightweight structure, but it's very strong. And chopstick seems to be, at this point, the right answer. So this series of structure analysis. And also, this is the mock-up that we built before the final within our laboratory. So the projection system is telling a student where to go, what the chopstick needs to be deposited at what angle. And following that, the guidance, without knowing what the final target geometry is, and you can print these the pavilion. And this is on the site. We found out very later on the projector needs to be dark. So we start working during the day and couldn't see anything. So all the construction, in fact, it took place in the middle of the night. This was something that we learned trying to develop that for the next project. So this is inside. It's a bit spiky to sit on it, but the kids loved it. This is right in front of our building, Tokyo University in campus. You can see that's the building behind it. So we have quite a few visitors, particularly nurseries and kindergarten kids during the day. So some pictures in nighttime. It's very poor, so the light come through. And it also coincide with the ginkgo tree that always turn yellow in a particular time. So as I was saying before, the student, when they enter the program, they don't know what they have to do in this time. Like, okay, we're building pavilion with 1 million chopsticks. So they develop it. They went through the technological skills as well as conceptual skill. They all learn through actual making. And then they also realize that things just doesn't work well. So they try to develop that when they are designing for the following year. So this is the upgraded version of that project. So it's the same, how to maximize human ability, but at the same time being supported with accuracy of computational processes. So this is called toca. Toca means Spanish touch. We have a Spanish student working on it, so it has to be. So I'll show you in the video later on too. So use the humans, this case, arm movement, very simple arm movement that could be very understood as repetitive, and in fact it's very repeating similar patterns. If you were to tell people to do certain things, perhaps we can look at it, some sort of patterns or habit or behavior. But the good thing about humans are they're all different in terms of size and they think in different way. So we thought, why don't we use a human as the differences, not as a negative, but as in a positive aspect. So in this case, swinging arm, everybody has different length of the arm, it produces different curvature, and maybe we can use these curvature for designing pavilion. So we measure everyone's in the studio, they act, like whole month, all they do is just making these particular patterns to become almost a kind of a part of the computational processes. So these are curvatures of the different student. Toka means touch, as I said before, so we try to make the kind of X-like shape based on their arm movement. And if you're to combine who is going to what part of cursor doesn't work this time. So we can say this curve is for him, this curve for her, this curve. So we can assign people where to go and what to do instead of we have to follow the idealized targeted geometry. We decided to use a spray form as the form of material. So spontaneously, it's like a drawing 3D in the real time. It's like a 3D pen that we have these days. But the spray form is it's dispersed, so we have to find a way to make it as a stick. So we did a series of tests. And also, once again, a spray dispenser. I mean, that's what we spend most of the time developing. How do you actually contain the spray? So there's a series of versions that we make in order to come to the last version. Similar to the last one, that is to say how to develop the system that has a real-time feedback process between the humans' movement and also a guiding system, where they need to go and what they need to do, and also structural analysis. Each time a student make, I wouldn't say mistake, but slightly different than what it intended, how to correct it. There's correct, you can take it down or just keep carrying on, but making sure structures are being updated. So this diagram shows it's a targeted geometry, and each step we make, but there's a correction processes that built in as a real-time mechanism. And the final geometry is close enough. Structurally sound, everything is fine, but slightly different. Is that a bad thing, or is that a positive thing? So we thought it was a positive thing that we can differentiate each time we make. So this is a quick sequence. Here's an idealized spray path. Of course, the student makes slightly different. So scan it, correct it. And then because this time we learn that in Japan, over 2 meters above, you have to have a license to do a construction process. So students are always working on the ground, and if they have to go up, we have to hire a contractor to do it. So in this case, we reversed it to say, why don't we use a light material? This is another reason that we chose the spray form. But we built on the ground, lift it up, so that we can constantly work on the ground, but that would create some more kind of inaccuracy in the process because you have to lift it up each time. So this is the left, on your left, that's the targeted geometry, and the right, that's what we printed it through the movement arm of the student. And the structural analysis, as I said, not happens before or after, but throughout the entire process is continual scanning and also analysis to take place. So here's some snapshot from the night view. Yes. I'll show you the video once again of this whole construction process. It's a tango, because we thought, how do you make a construction process like a dance, right? The person comes together in the print. This time, instead of projection, we use a QR code so we can see during the day. It wasn't as smooth as what we imagined, as you can see. Okay, now time is almost up, so I'm gonna be very quickly. A sustainable prototype. So what I showed was the architectural prototype, how to explore the idea of materiality, fabrication system, geometry, construction processes, all that. But we haven't really dealt anything what we consider as an architectural issues, the site, client, economy, all these things. So how does it all relate? So the second year student, they take this first year project as a basis and apply and find the site in Tokyo. Since time is quite running out, so I'm going to be very quick to show some of the example, what are the kind of things that we're working on. Typically, architecture is the end of the architectural production, and that's it. And then particularly in Tokyo, where the building lifespan is about, for house, 10 years. After 10 years, house has no value if it's in a wooden building. Steel building is about 30 years. That's the lifespan. So there are lots of construction processes going on, but at the same time, there are a lot of waste that comes from this construction. So how do you deal with this whole issue of making and then remaking architecture in the city in Tokyo? And Tokyo is also a great, maybe this is Japan, maybe Canada the same way, but the recycling process is very, very efficient and effective. You cannot just throw rubbish into the same rubbish bin. You have to separate them. Paper, plastic. If it's can, you have to separate in different ways. So great, but how do you make the whole material circulation processes not always going back and forth between the product and the raw material back and forth? Is there any way this whole circulation of material as a part of the architectural processes? So this is a kind of rough diagram. Instead of going back into a raw material, how do you use the material as a potential transformational processes where architecture happen to take place within this material flow? So in this case, typically paper from tree goes to waste, and recycling happens in this way. But how do you make an architecture as an additional to the whole material flow in the city? So we explore whole different ideas, materials that are not considered architectural materials. I'm going to show you some samples, like wasted coffee ground, or the paper is perhaps more kind of known for recycling, but not from the architectural, or something like hair. When you go to beauty salons or barbershop, you get your haircut, but what are you going to do with the hair if it doesn't have any architectural possibility? So students are kind of wandering around to see how do we rethink about material and how do we maximize the material that is available in the city, where materials are being produced in the city rather than only consumed. Quickly going through, this is called digestive architecture. Internet economy really produce a new type of material distribution, and the output of this is a cardboard, where you buy something in Amazon, there's a box within a box in the box. You always get the cardboard all the time. And this is actually Canadian studies. Students are looking at the cardboard as something the city produce all the time. Can we do something without turning that into toilet paper? In Ontario Agriculture Department, they study that cardboard can be replaced for cow feed. As long as there's a 40% nutrients are provided in addition to cardboard, the cow can sustain perfectly healthy. And we thought, what a great idea that we can turn the cows into this whole material transformation process. So architecture in this case happens from not only about cardboard back to cardboard raw material and then end up in toilet paper. In this case, it's a tree that provides a material for, but instead of going industrial process, it goes through the agricultural process. So the cardboard is fed using for the feed, but what a cow produces is cow dung. Now you can turn the cow dung into fertilizer, but there's a very enriched fibers in it that we can turn that into brick. And the brick will become architectural material. If you don't fire it, it becomes the once again, the raw material again. So you can begin to produce this kind of material cycle from the cardboard to the feed for the cow, and the cow will produce an architectural building material, and you can use it for making temporary building, and in the end, you can bring it back to farmland where it becomes a fertilizer. So student, in this case, is really got the cow dung, making their own brick, testing out how much fiber it needs to in order for that to become a sustainable product. So our studio, you can kind of imagine what the smell like. And you looking at this on the left is what they do in the first year. It's about whole geometry, how to put together different type of material that through one single production process that produce various different components. But depending on how you put it together, you can control the outcome. So it's a kind of reverse engineer. You want to have an output in a particular way, find these curvatures, and you can stack it in a kind of puzzle in order to create some geometry in the end. Or if you fire it, it becomes some of the places like India and other places, they use it for the kitchens, a fuel. So it's not only about going to the fertilizer, but you can also turn that into potential emergency fuel. So these are the kind of things they do in the first year, geometry study, but then geometries are also tied back together with the material system. In this case, is how the city produces a particular material that works in a larger agricultural as well as urban system. And so the final proposal for the student was to create a farmer's market where they use it only in the summertime, and all the material out of the cow dung is used, but then go back to the farmland in the wintertime, and then the cycle produce again. This is another project. This is typically cities are quite polluted. So the more construction process take place, the city get quite toxicated or polluted. So how do you reverse this concept of more buildings are being built, perhaps the healthier the soil, healthier the ground will be? Is that possible? So this project is generating this brick that comes out of the gas station, where gas station in Japan, I forgot exact time, I think it's 30 years or 25 years, that's the maximum license. And in order for the license to be re-granted again, to renew for the gas station, they have to take all the soil out, clean up, and then put the soil back in, and then do another kind of run of a gas station. Nobody does it because it's too expensive. Typically, they just put the soil back on, and then put the building. Nobody knew what it was before. So the places in Tokyo, many places are very, very polluted. So how do you deal with this issue of polluted soil? And the student found out that there's enough microbe, enough air, all of those. If you put it together, these gas, the toxin, could be evaporated. It could clean itself. So this developing this brick that can put together to create a series of pavilions. So once again, these are kind of student projects that generate the geometrical system, but also deal with the issue of a city, in this case, is how to deal with a polluted ground. Similar idea that because the geometries are being put together in a very simple way, but they're all different, differentiated geometry. If you put it together in a certain way, that they can control a particular outcome. So those are the geometry they can produce, also the system. So the proposal is to work at the various construction site as a let's just say post-gas station construction site. So they dig it out, the whole soil, they pack it into a series of these trapezoid-shaped brick, and they can create a pavilion. In the meantime, pavilion will detox, if you like. And after a half year, the soil becomes clean, and you can put that soil back in, basically demolish the building and put it back. So the architecture exists within this material transformational processes rather than the architecture always is an end means. So here's some of the proposal. Now, the last images I just wanted to show is the idea. This is a bit radical one. We don't even know what to do with it at the very beginning. Coffee grounds. Everybody drink coffee. We don't think second about what the potential of the coffee ground. But the coffee ground has an incredible properties that is fire resistant. It observes the odor and also produce the aroma, and also repellent for mosquitoes and all that. It's a kind of incredible property, but can you actually network all the coffee shop in Japan or in Tokyo in order to collect all those to produce an architectural building material? I mean, that's what the student tried to do. So here's the final the images. Let me just get out because I couldn't get to. Let me see. This is the sample video. Where was that? Yeah, this is a bit of a teaser, so it doesn't really.
Intimacy Cloud is an urban intervention that provides multifunctional space for local people to strengthen the quality of Roji, both culturally and physically. Located in Roji, a small traditional wooden house alleyway, the place where public and private are merged. This maze-like district is rich with diversity. The area was gradually disappeared from the lack of urban safety. People are struggling to maintain their old lifestyle. To intervene this culture district, we look into one unique culture called Kodawari. Kodawari is translated into the sensitive to a minor thing or the power of detailing. We use this culture as a medium to bridge urbanism and people. Coffee culture, as it is subtle and always changes itself to serve developers. We choose coffee ground as a material with its multiple potentials: fire resistance, odor absorption, lightweight, and pest repellent. It provides a significant benefit for Roji. Within Roji, Intimacy Cloud extends from cafe while acting as a fire retardant, absorbing odor from smoking area and distributing coffee aroma. Coffee ground component is weaving into the volumetric cloud, creating the seamless space. The component can be pre-programmed to respond to the environmental condition, varies in porosity and area surface. The geometry is curated from natural condition, sunlight, airflow, olfactory, and visual connectivity. The voxel system deforms according to the solar radiation to create the light and the shading. Airflow calculation is introduced to create a continuous interior space, guiding aroma and smoke to travel within void space. Olfactory optimization seeks to gather the aroma particle to create the atmosphere. Visual analysis organizes the porosity of components to create the network of visual connectivity. Coffee ground is hybridized with wood frame to help control the overall form. Coffee composite is a combination of coffee ground, vinegar, agar, and water to create the lightweight shelf material. In the drying process, component has ability to warp from flat domain to three-dimensional forms by shrinking. We can pre-program the movement of component to let the component adjust itself when connected into weaving structure. Intimacy Cloud is a material-driven architecture. More material consumption resulted in the further progress of architecture construction.
Okay, with that, I'm going to leave it here. Thank you. If I add the very last one, the context is it's a downtown Tokyo where it's survived the World War II. So, but because mainly very tight, Roji means very tight alleyways, very interesting neighborhood, But because the fire regulation mandate all the buildings be demolished, it put one of those high-rise buildings. So what are the reasons for demolishing is the fire? So what are the kind of different material rather than concrete that we can call it a fire resistant? So the coffee bean became the driving force for generating project like this. And also people realize that it's very interesting places for creating this very Japanese, I guess, is very detailed craftsmanship people. So the coffee, it's not just a cup of coffee, but excellent, all different exotic coffee they make. So, culture and also the urban issues and also the kind of local residents, how you synthesize those, but through not only about design proposal with idea, but also the digital fabrication that comes in order to make those projects possible. Thank you.